All right, we'll go ahead and get started here. First of all, thank you all for joining us today for TC's Monday webinar. Today, as you can see, our topic is hydronic snow and ice melt design. This will apply most generally to all snow and ice melt design, but our examples on the loading and whatnot will be based around hydronic selection and selecting flow rates and whatnot. So I will touch very quickly on electric, but for the most part, our presentation today will be solely hydronic. And let me get the presentation up here for you. Okay, today's presentation will count for PDH credits for Illinois and Wisconsin. It is only for the live version, so unfortunately if you're watching the recorded version of this, they will not apply. And as part of that qualification, we will have a few questions as the poll questions, I should say, as the presentation goes on. And the software will also be measuring your interest rating or participation. So if you're checking email and whatnot in the background, it will pick up on that. So if you do need the credits, please pay attention. Make sure you fill out the questions as we go along. If you have your own questions, please feel free to enter them in the chat box or question box at any time, and I will try and get to them when we have those poll question breaks or as we go along if they apply correctly. And as I mentioned, this is being recorded, so it will be available on our website for future viewing. If you have any issues with the sound or whatnot as we go along, please feel free to make a note in the chat or question box about that as well. All right, today's information is going to be as generic as I could possibly make it. I do have some excerpts from Rejo, which is a manufacturer that we work with, but all manufacturers of snow and ice melt equipment have similar resources available. So again, it's not driven by any specific manufacturer. And then a lot of what we are being will be discussed today is out of Chapter 21 of the ASHRAE Handbook, the HVAC Applications Handbook, I should say. That was last copy came out in 2015. So if you have any questions, you can always refer to that material as well. But hopefully this will give you a more understandable overview of that material. So first and foremost, why would we want a snow melt system? The first and foremost use is convenience. I mean, we can obviously move snow other ways, so the reason we're doing it this way is out of convenience. And some other options and reasons we do would be safety, preventing damage and maintenance, and reducing liability to the owner. There's a plethora of other reasons as well, but usually those are the most listed when you talk to owners and whatnot as reasons why they want to install them. Safety and liability, especially if they have ramps or trouble areas, and then damage and maintenance, especially related to salt. You're not having to first and foremost pay for the salt and someone to apply it, but then you don't have to worry about people dragging snow, ice, salt, sludge into your building. And this last point here, depending on your system and how it's applied, may or may not be true, but there are, in a lot of situations, a reduced cost to implementing a hydronic snowmelt system when comparing to paying for someone to remove it for you. So if you're shoveling your own driveway, you're obviously not going to get any savings, but if you're in a commercial setting and you're going to be paying a service to come out every time it snows, depending on the situation, it can definitely reduce your service costs. So where can it be used? Well, pretty much anywhere that you can fit the tubing for it, whether it's in a slab or a sand bed beneath pavers, which are the two most common installation techniques. It can go anywhere those surfaces are available. Here's a list of common ones. The most common we would see would be outside of medical areas or medical buildings, hospitals, ERs, senior living, anywhere that liability is even more important than a standard building. It can also be used around pools and spa decks that get used in the winter, although that typically ends up being more of a radiant warming situation. Places we don't see them as much but would make a ton of sense would be airports, car washes, although we do see the exit areas around car washes implemented to prevent freezing, but certainly not as much as you'd expect. More popular these days I've seen are intake plenums and penthouses around air handlers to prevent any snow or ice from building up around those areas. Those have become extremely popular on buildings. All right, so let's start by getting in the design process. The first thing to note is that we cannot design a system that's going to allow or account for all weather conditions. If we have a once in 30-year blizzard, even the best and most robust snowmelt system is going to have issues keeping up. So we have to have a new, or not a new way, we have to have a way of defining exactly what our load is going to be. So different things that affect your snowmelt load be the air temperature when it's snowing, the rate of the snowfall, the wind, humidity, slab temperature at the start of snowfall, the type of slab you're using or surface. So even beyond these, there are many different factors that affect the load. And the way we're going to address the design process today or walk through it will be the installation strategy, the design of the actual loading, and then we'll talk about the heat source and different ways to control it. So the best way to go about designing a system, in my opinion, is to see how feasible it is and what type of installation you're going to use before you even get into the loading. If it's not feasible, if you're not going to be able to set it up in a way that makes it worthwhile, there's no reason to go any further as far as the design. So the first thing you want to identify is what type of surface you're using. The most common, as I mentioned, is a concrete slab or a concrete overpour of an existing slab that'll have the tubing encased within it. The other main applications for a hydronic system, at least, would be asphalt or a paver of some type, or if it's going in a athletic field or whatnot, it would be grass. In each of those last few cases, the tubing is getting encased in a sand bed beneath the surface that goes over the top. So in those are your most those are the most common ones, obviously. If you have another application, you would want to check with your manufacturer to see if it's something that's an option. But in the case of hydronic PEX tubing, those are your biggest surfaces. And then in related to that, how are you fastening the tube? In concrete, it's most likely just getting strapped to the rebar, some wire mesh. But depending on the application and the surface, there will be some different fasteners. We'll talk about insulation a little bit later, but in most cases you want to put insulation beneath if possible, as long as it's not going to affect the drainage. You want to make sure that where you're melting snow, you have somewhere for all the moisture to go. So you want to make sure there's drains or it's sloped away into landscaping. so that no water can dam up and then create an ice bridge or any other issues. And then in terms of location, you have to be able to make sure you can run the piping to the surface area and then back into your building or wherever your heat source is located. In addition, the shape of the area and the farthest point from the manifolds are things that have to be considered with the length of the loops and whatnot. So the first and foremost, as I keep saying, is to make sure it's feasible. Make sure it's an option that'll work. I have one question here about the depth of the tube underneath the various surfaces. In general, when you're using a concrete slab, you want it to be, the manufacturer will say that you need at least 2 inches over the top of the tube in a structural slab. If it's a topping slab, I believe it's a little less than that. And then in terms of pavers and asphalt, you do want some sand covering the tube, but it's not 2 inches. In that case, you want to refer to the individual manufacturer. I can pull out a diagram towards the end of the presentation if we have time to go through that a little further, but let me keep going here. So here are just a few simple applications that I'm sure you've seen. A lot of the top right and bottom left are ramps. Those are two very huge ones, especially in cities, going into lower parking areas, and then just sidewalks and driveways in general. Here's a couple more installations showing the tubing. Here on the left you see a trench drain, very important, especially on ramps. Usually just one large one at the bottom, but depending on how big a drive. This one on the left is actually from a larger street area, so that's why they have one in the middle there. And here's a little diagram for a standard concrete slab, as I mentioned, showing 2 inches over the top and then plastic ties tying to wire mesh. Just another quick picture, and along with this picture, this is a good application here because otherwise you'd be driving snow trucks in and out here. You'd have people shoveling sidewalks and whatnot, so it certainly saves a lot of labor. All right, so the next step in the design is to look at the actual load, and the way that we do that with, or the way that ASHRAE has tabulated that is what they call heat flux, and it's basically the rate of the heat flow per unit of surface area. So BTU per hour per square foot. And ASHRAE, as I mentioned, the Chapter 51 provides calculations or equations to calculate all these, but thankfully they've also tabulated these into different tables. And the first table that we'll be looking at, they've tabulated using snow-free area and frequency distribution. You may be familiar, they used to, several renditions ago, it wasn't 2011, it had maybe 2007, they switched from a class rating, which was class 1, 2, and 3, to this new system. So we'll go through this real quick and make sure everyone's familiar. Snow-free area is basically calculating the amount of snow coverage. Well, it's not really calculating. It's a figure showing the amount of snow coverage during the snowfall session. So it's basically saying how much snow are we going to allow to accumulate while the system is working. And so while you're melting it, if you were in a critical area, say a helicopter pad or whatnot, you would want a snow-free area of 0, meaning no snow, or I'm sorry, yeah, a snow-free area of 1, meaning no accumulation during the snowfall. If it's a driveway or a residential area or a commercial, side area that does not need to be critically melted during that snowfall itself, then you could go with the snow-free area of 0 or 0.5. But if it's critical and there can be no snow accumulation during the snowfall, then you would want to go with 1. And here's just a demonstration of this. So on the left, this is a snow system working as the snowfall is coming down. There is some snow accumulating. On the right, it's basically saying, it's showing once all the snow, or once the snowfall is stopped, the snow system quickly recovers and melts the remaining of the snow. And here's what that table looks like. So the first column here is snowfall hours per year, and this is data tabulated from 1982 to 1993. And then the second column is the snow-free area we were just discussing here. And so once you decide what your snow-free area is, the second element there is the frequency distribution. And if you look to the next several columns across, this is heat fluxes not exceeded during the indicated snowfall hours. So basically what this is saying is for a given snow-free area, the percentage of snowfalls that would be covered or included within that distribution. So if you look at the bottom, I hope it's not cut off for any of you guys. The last one here is Chicago, Illinois, O'Hare. You know what? let's use the first one as for this example. For Albany, New York, if we have a snowfall area of 1, so at 90%, it'd be 125 BTUs per hour per square foot. So that's saying if we design our system at 125 BTUs per hour per square foot, it'll cover 90% of all snowfalls with a snow-free area of 1. So for 90% of all snowfalls, no snow will accumulate during the melting with that system. Now, if you notice, if you go to, let's say 98% and 0 snow-free area, that's at 119. So if you designed your system for 125, oh, I'm sorry, let me go back to the correct chart here. Your snow system is still going to have a lot more coverage, just it'll be allowing enough snow to accumulate, if that makes sense. So even if you design your system for a snow-free area of 1 at a given percentage, it'll still be operating the whole time, even if snowfall is accumulating for that crazy blizzard, that covers that last couple percent. I hope that made sense. If I can clarify that once we get to a poll question if needed. All right, this is a bulletin from Rejo. As I mentioned, most manufacturers will have their own tabulation, but this is just basically giving you a guideline of what free area ratio and what frequency distribution you might want to use based on different applications. So we can do a quick example just to go over this. To keep it simple, we'll look at 1,000 square foot sidewalk for a Chicago apartment building. So if we look at the tabulation we just saw from Rejo, they recommend my apologies, over-clicked. We have a free area ratio of 1 and a frequency distribution of 98%. So if we go back to our heat flux chart from ASHRAE for Chicago, Illinois, O'Hare, at a 1 snow-free area ratio and a 98% frequency distribution, we have 186 BTUs per hour per square foot as our heat flux. All right, so now that we have our heat flux selected, we need to calculate the total melting load. And that equation looks like this. We're basically adjusting our heat flux and area for a back loss charge. And back loss is basically how we're estimating the downward heat loss and edge loss for the system. Rejo typically says that it's typically a 20% loss with R10 insulation. That's their estimated figure. It certainly has some safety factors built into it. It's obviously hard to say or calculate what this might be. They do have it. They've tested it certainly in different applications and tabulated that data, which is where they came up with that percentage. But it's obviously variates a lot based on soil conditions and application. So we'll go with their 20% here, but that is a tough number to estimate, just for your future reference. So for this example, 1,000 square feet and our heat flux that we've taken from the table and the back loss safety factor, our melting load is just over 200 MBH. All right, let's stop real quick and do our first poll question here. If you have any questions over what we've gone through so far, feel free to type them in as well, and I will try and answer them. All right, you should see the poll question here. What is the heat flux in terms of snowmelt system calculations? And then a couple options there. All right, it looks like most of you have voted, but please try and get them in the next 30 seconds or so. All right, give it another 10 seconds here. Make sure you get your answer in. Well, you guys are finishing that up. I did get a question here related to the costs. I will try and address that towards the end here, but there's not exactly a great way to estimate material costs without looking at the specific application, just because of how variable each system can be. Like I said, I'll try and address that a little bit towards the end here. All right, I'm going to go ahead and close this up, and we'll get moving here. The answer for that one should have been B, the heat flow rate per unit surface area. All right, so the next step, once you have the melting load, would be to look at the heat source. So in addition to the melting load, we'll look at the pickup load and your options of idling, and then look at some different heat sources here. So the pickup load would be the energy required to bring the system up to melting temperature, which is typically 38 degrees. 38 degrees surface temperature, not a slab temperature. And the pickup load can either be from a cold start or an idling temperature. So we'll talk about some control schemes a little bit later, but basically you have the option to idle the slab at a median temperature to allow the pickup time to be shorter. You definitely want to consider the pickup load when you're tabulating the melting load, and depending on the system, it may or may not be a requirement or the amount of pickup that you want to allow, I should say, will be variable on the type of system. because it is going to oversize your heat source to some degree. So if you're trying to do this for a residence or a non-critical area, the pickup is a little less critical because you're able to allow for more time for it to melt. If it needs to be ready, at the second the snow starts, like a helicopter launch pad or whatnot like that, then you want to look at idling and maximizing your heat source for pickup. But we will do a example here so you know what to look for here. All right, so we're going to be looking at a concrete slab just to keep things simple. And for concrete, on average, it's approximately 30 BTUs to raise 1 cubic feet 1 degree. So we'll use the following equation here, which is basically taking the area and then the load to calculate our total pickup load. So for this example, we'll go back to the example I used previously, which was 1,000 square foot Chicago sidewalks. And so our pickup delta T will be our starting slab temp, which we'll estimate at 18 degrees here. And then the melting temp, surface temp, which I estimated at 38 degrees above here. And we'll use a 20 degree delta T. And then our BTUs per hour per square foot for warm up, and a back loss of 15. I apologize. Let me go back. Where is this bouncing around? Sorry, give me just a second here. Okay. And in this example, I apologize. I only used a back loss of 15% instead of 20. So sorry that's not consistent. But at any rate, as you can see, the pickup load is almost the same load, or the same as our melting load, 230 MBH. So if we sized our heat source purely based on the melting load, in this situation with the pickup load, our pickup would be about an hour, since they're roughly the same size. It'd be slightly over an hour. And so for this application, since we're in just a simple sidewalk in a downtown area, allowing a 1 hour for the slab to get up to full melting temperature is perfectly acceptable. When you get into larger thermal masses than 1,000 feet or different situations, it will make a difference. But I had a couple questions here. Where'd you get the 18 degrees? The 18 degrees, I'm going the wrong way. 18 degrees is the starting surface temp for the melting. And that was selected, which is not listed here, I apologize. That was selected based on the temperature of the slab when it starts snow melting, and that's that is from the lower end of the temperature from which snowing can occur. So if it's 10 degrees outside when the snow melt starts, or when the snow starts falling, sorry, I'm mixing my vocabulary here, the surface temp is 18 degrees, and that's where that came from, when it needs to get up to 38 degrees to be melting. The follow-up, these numbers are not additive then. Yes, if you, let me see if it's listed here before I keep talking. No, I don't have a slide on it. So I can address this towards the end if I need to. The pickup load would be additive if you wanted to completely account for it while you're as part of your heating load. In this case, we're okay with it being the same size as the melting load, so we would not oversize the heat source. But if you were going to account for it, you would want the heat source to be able to account for it, or you would need to idle the slab with controls. All right, now in terms of what you can use as the heat source for the snowfall or the snow melting system, obviously a boiler system is the most common. And if you're using a boiler or a boiler system that has higher temps, you will need to supply some mixing. Typical temperature requirement for the supply water is around 120 to 140 degrees, although if the system is designed accordingly, it can be lower than that. So in addition to your typical boiler systems, you can use all sorts of different heating sources, obviously, as long as you can provide those water temps. So they could be chiller tower water or heat recovery from a chiller itself, electric boilers, obviously, or heat exchangers, siphoning heat off of anything else you're trying to dump heat. This is just a quick note. If you're designing a system with a non-condensing boiler, not only do you need to mix the temperature so that the snow melt is protected, snow melt system is protected, sorry, but you also need to make sure that the boiler is protected. So you want to use a 4-way valve instead of a 3-way valve to make sure that the return temp to the boiler will not put it into a condensing situation. All right, let me go to the second poll question here. All right, the second poll question, which should be launched now, is the pickup load is. I didn't define this particularly well, so I'm going to give you the correct answer is A, the amount of energy needed to bring the thermal mass up to temperature. When I get to the end of this, I'll go back over the pickup load briefly, just because I did not explain that very well. Yeah, if you could go ahead and select A, and let me see, give it another few seconds here, and then we'll get back started. All right, it's only showing that 90% of you have voted, so I'll give it a few more seconds and then we'll keep going here. All right. All right, the next, let's talk about controls. Okay. Now, as far as controlling these, we can go anywhere from an on-off switch to a full automated control. And now a lot of the controls are starting to be able to integrate with backnet systems or other building automation systems, which is absolutely fantastic. But let's start at the bottom here and kind of move up. So the manual I have crossed out here, you should never offer to design a system that way or for any reason. At the very least, you should go one step up to a timer so that the system can never be accidentally left on. Snowmelt systems do use quite a bit of energy to run. So if you leave them on overnight or something with a switch, you're talking about a huge gas bill the owner was not ready for. So at the very least, a manual timer is great. If you're doing a residential area, such as like a area around a spa outside or whatnot, a timer is a really great option because it's obviously very cheap. They can turn it on for a couple hours before they need to go out there or plan on go out there, and then if they forget to turn it off, it'll turn off on its own. For any other system, though, you should be looking at a semi-automatic or fully automatic control system. The main two systems you'll see are either like a slab-mounted moisture sensor or an aerial type snow detector. And then the control that associated with them. We typically see Tecmar the most, or ETI, but there are other brands out there, of course, for each. Most snowmelt manufacturers either produce their own or rebrand their own OEM style. Quickly, I want to touch on IECC 2015 changes that apply this year for Illinois. Basically, what they're requiring is that there is some mechanism to shut off the system when the pavement temperature, surface temperature is too high, and then another mechanism to basically turn off a control when the outdoor temperature is above a certain degree. So your control for both residential and commercial needs to address the outdoor temperature and the slab temperature, which is the second of, well, the slab temperature has not always been included in that code. So what that means is, quickly here, the left is what they call like an aerial sensor. So it's mounted outside, either on the top of a building or on a post or whatnot. And when snow starts falling, it collects snow in the cone on the top here. And then there's a sensor pad on the inside that senses the snow. If it senses the moisture on the pad and the outdoor temperature is in the correct range, then it'll activate the system, and it'll keep running until it does not sense any more snow falling. And then this particular control will run the snowmelt system for a set number of hours afterwards. So this particular control, I think, defaults to 3 hours. So basically, once it senses that snow is falling, it'll turn the system on, and then once it senses when it's off, it'll run for 3 hours and then shut it off. The one on the right here, you may have all seen. It's like the hockey puck style, if you will, that gets mounted in the actual slab or embedded in the surface. This sensor detects the moisture directly on the surface, and then it also has a sensor that measures the surrounding slab temperature, and it is used in accordance with a control that also uses a separate outdoor sensor. So the system on the right is extremely more expensive, but extremely more accurate or more interactive. I started to say that on the left, the control on the left now requires you to also use a secondary control, such as like a Tecmar 151 or 152 slab sensor that's monitoring the slab sensor as well. So you would want to put those in series. So those are the two most robust and most common snowmelt sensors. Okay, we had asked a couple questions earlier about material costs. Again, I'll see if I can get to that at the end, but quickly we're going to talk about the operating costs, and we're going to pick up our example from before where we had 1,000 square foot sidewalks. You'll notice on here that electronic control with no idling. as I mentioned before, idling is a way to basically preheat or pre-warm your slab. So as I mentioned, like we're looking for a 38-degree surface temperature for melting. This would basically you could preset the temperature, but this would basically keep your slab at 25 or 30 degrees so that once it detects that snow melting is falling, it can warm up easier. And that would be a function of the controls that we just discussed. So if you go back here, your fully automatic controls. So if you're familiar with Tecmar, that'd be like a 665, 667, or 6880 control. We'll have a lot of those features such as idling, setback, multiple sensors, different types of modulation and whatnot. All right, sorry, let me get back to over here. All right, and as we mentioned before, we'll be using ASHRAE data. This is actually referring to Table 3, and although this shows 2011 still, this table is also in the 2015 version, I believe with no updates to it. All right, so our annual melting load is going to be our, sorry, let me briefly go back here. So from Table 3, it gives you the melting and idling requirements in hours per year and BTUs per square foot based on your location data. And the data we selected earlier, the air-free ratio or the area-free ratio and the frequency distribution. So this is telling us that we need 124 melting hours per year, or that there is 124-hour melting hours per year in our area, and that the yearly load would be 8501 BTUs per square foot. So if we go and apply this to our melting load and our pickup, we're going to have basically 8.5 mega MBH and 2.3 million BTUs for the pickup load, giving us a total annual load of just over 10 million BTUs. So for our example, we need to convert this to cost now. If we just assume $1 per therm to keep things simple here, our total annual cost comes out to $113 basically per year in operating costs. Now with idling, if we had idled the slab at 28 degrees, that means our delta T from the surface temp to our starting temp is only 10, therefore cutting our pickup load in half. But if we go through back to Table 3, it has additionally loads tabulated for idling. If we were idling the entire season, we'd be adding quite a huge load to our yearly load. As you can see, we'd be looking at 116 million BTUs per year in idling costs. So it doesn't make sense in a small situation like this, but if it's super critical, or if you wanted to provide it to the owner as an option, you just need to make sure that they're aware of the severely increased cost of idling. And as you can see down here at the top, it's basically a tenfold more expensive than our standard example there. All right, so now that we have the load identified for our system, and I will give you a couple rules of thumb to apply to that at the end here. But now we need to look at sizing the actual loop field for the hydronic system. So the first way to start this is to figure out your system flow required based on your load. Now, it's kind of circular here in the fact that your selections for tube size and whatnot will affect your pressure drop and velocity. So you may need to make a selection, go back, check your flow and pressure loss, and then maybe select a different size. I'll give you a couple of guidelines, so hopefully you won't be doing that very often, but at any rate, things that we need to consider here would be glycol concentration and delta T right off the top. We typically recommend designing the system at 20-degree delta T. If you go up to 30 or so, 30 is certainly an acceptable value. However, while the system's warming up, it creates a much larger delta T. So we recommend designing at 20 degrees to give you an overall system that'll, even if it ends up operating closer to 20 or 25 or 30 degree delta T in the field, will still give you an acceptable delta while it's warming up, as well as slab temperatures. All right, your basic formula for GPM or flow calculation, as you've seen here, for 50% propylene glycol, these are the exact parameters, but it's roughly accounts to a 10% increase in the flow. Oops, sorry, let me quickly go to poll question number 3 here. Sorry, I'll try and keep us moving along here quickly, so I'm not keeping you guys all day. Which of the following is not a recommended control scheme for snowmelt systems? I'll give you about 30 seconds here. Okay, we haven't really gone over 92% of you guys, so I'll let that close that up. The correct answer here would be B. We do not want just an on-off switch for a snowmelt system. All right, moving forward. Okay, just to continue with our loop field sizing, typically for snowmelt systems, you don't want to be smaller than 5/8 inch tubing, simply just to minimize any problems with freezing or thickness due to glycol. And depending on if you need to go to a longer loop length, then you would go up to 3/4 inch or even 1 inch, depending on how large your system is. We're typically looking at loop lengths between 200 and 300 feet and spacing between 9 and 12 inches, or I'm sorry, 6 and 12 inches. We typically design for 9 inches on center spacing of the tubing. The spacing is going to change based on your load and your pipe diameter, depending on if you need a higher heat flux, you're going to have to tighten the tube spacing and go with a larger tube in order to get the amount of heat pushed into the slab. And then to keep pressure drop down, you may also have to go to shorter lengths. And another thing to consider is with the manifolds, your pressure drop coming back through that header. Manufacturers, the pre-assembled manifolds are all tabulated, so you can pull those when you're doing the design. But if the contractor is going to be installing the hand-built copper manifolds, that's something that you want to make sure is accounted for as well. So this is another chart from Rejo, but again, most all manufacturers will have all of their data tabulated. As you see here, the first column or the first section of columns is the flow velocity, and then it goes by temperature and pipe size and whatnot. So up here we have head loss at 50% glycol. So as you can see, it's just tabulated. Each column is pipe size, and then the flow on the left here. Going back to our example, we had 1,000 square foot. We had calculated 25 GPM. So we'll start with a selection of 5/8 inch PEX, 200-foot loop lengths, and 9-inch spacing. So as you see here, we'll need a total length of pipe just over 1,300 square feet, or 1,300 feet for our 1,000 square foot area. And that comes out to just about 6.5 loops, so obviously round up to 7 loops, which gives us about 190-foot loop lengths, and each loop will have 3.61 GPM. So if we go back to our head loss charts, we're going to be either with 5/8 inch will be just over around, let's see, we were at 3.6, so we'll be closer to 16, 18 feet of head loss per 100 feet of pipe, which is pretty high. So in this case, we would probably want to move up to the 3/4 inch, which is only giving us about 6 to 8 feet of head loss per 100 feet of pipe. As you can see here, 5/8 is not acceptable. So for our 200-foot loop length, we're dealing with 16 feet ahead in this design scenario. The next would be to calculate the manifolds. Again, this is tabulated from Rejo's manifolds, but all manufacturers have those shown. So we'll be doing the 5-loop manifold with the log chart. So we're at 25 GPM on the bottom, and as you can see, that's about 15 feet ahead, or I'm sorry, 10 feet through the manifold. So for our final system, we'd be looking at 25 and some change GPM at 26 feet ahead from the manifold on. So any piping before that needs to get added on. And then our load, as we determined earlier, is around 230 MBH. So we'd be looking at probably a 250,000 BTU 95% boiler if we were going with a traditional heat source. And then our 7-station manifold with 3/4 inch pipe and 200-foot loop lengths. All right, let's quickly go to our last pull question so I can get you guys going here. This is our last poll question, obviously, and I will try and wrap up pretty quickly. I know some of you guys have places to be. I'll put my email back up again at the end, but it's lewis.mino@techmungo.com, tecmungo.com, if you have any specific questions for me. And Yeah, I'll try and cover a few more things, but if you need specific questions, let me know. All right, let me close this up and just go through a few quick little things. Okay, as I alluded to, some rules of thumb. For the Chicago area, we found that designing at 125 BTUs per hour per square foot for non-critical areas, meaning not helipads or anything else like that. But this will cover, stairways, ramps, drives, commercial and residential. You can certainly design to a lower value if it's a non-critical residential area, but we find that 125, it's basically a number encapsulating the heat flux tabulated for Chicago by ASHRAE, but also factors in some back loss and glycol calculations. So it's kind of a good quick number for estimating and designing systems. As I mentioned, we like to design to 20-degree delta T. That way, if your system's a bit undersized, you have some flexibility to basically drop the flow rate slightly to go up to a higher delta T to get a little more juice out of it. Basically allows you to, a little extra safety factor. Let's see here. And then as I mentioned, 5/8 inch tubing, 200-foot loops, and 9-inch spacing is usually pretty sufficient up to around 3,000 feet. At that point, you're getting to a number of loops where going up to 3/4 inch is probably the best way to go, just simply to eliminate how many loops you have to install. The other reason you might do that to go with a longer loop length is if it's a long walkway and where you can mount the manifold. Insulation options. You're all certainly familiar with rigid insulation. I'm sure a lot of you are also familiar with the poly like bubble options. We typically recommend the poly bubble with the radiant lining, the aluminum lining in it, but it can certainly be either. There's no code requiring one over the other. There is code come with relation to insulation, more geared towards radiant installations, but in either case, they have to do with they usually just require edge insulation at the slab. So that's something to double check, but usually not a requirement specifically for snow melt. Another couple other things to consider is to make sure that whatever system you're using, they have some sort of fitting or repair that can be buried in the concrete. This one shown here is Rejo's Everlock fitting. As long as it's wrapped in tape, it can be buried in concrete. So if someone cuts into your slab or there's otherwise a leak, you want to make sure you have an option there. Over here on the right is Rejo's Insulpex. Again, most manufacturers have these available where it's pre-insulated. It's a good option, if you have a slab that's away from the building and you need to run the supply and return to the manifolds out there. Glycol feed systems, obviously the systems need to be glycol. In most residential and commercial systems, we're typically recommending just a small residential style feeder. You do not need to go with a full overblown thing. My email is shown here at the bottom, so please feel free to contact me directly with questions. I will, if you posted a question in the box and I have not had a chance to answer to, I will make sure to answer to you directly via email. And I believe that's it. I will, if you guys have any other questions, feel free to ask now. I have one, how is the tube protected in the concrete? Most PEX tubing does not need any special protection, except when it's coming in or out of the slab. So if you, and most manufacturers supply it with it, but usually they just use a piece of PVC to sleeve the tube coming in and out of the slab. But within the actual slab itself, it does not need any additional protection besides the barriers that the manufacturer creates. You do, however, want to make sure it has an oxygen barrier. All PEX tubing you're installing these days should definitely have an oxygen barrier to prevent it from degrading over time while it's in the concrete. I had one other question regarding standard 90.1. I don't know if ASHRAE specifically addresses any snowmelt requirements in there. I will double check though and get back to you on that. Drainage systems for residential type uses. With residential systems, you don't need to be, or you don't need to necessarily install anything specifically. If it's on a driveway, you just make sure everything's sloped away so that the water has somewhere to go. If it's a residence where the drive is going down towards the house, then you'd want a trench drain down at the bottom. But just making sure that slabs are sloped away so that the water has somewhere to run. If it's on a flat surface and it's just pooling water, as soon as the system stops, it's going to have. I had some questions on the PowerPoint itself. If you email me, I can send you a copy of it. It is kind of big, so I can Dropbox it if I need to. Otherwise, the presentation as a whole will be posted to our training website. Where do I get the heat flux tables and design parameters? I'll make this copy of my presentation available, but in terms of the heat flux tables, those are from ASHRAE, the ASHRAE handbook. Let me go back to the front here. It's the HVAC Applications Handbook, Chapter 51. The last one that came through was the 2015 update. All right, I'm going to close it up here. I really do appreciate you attending, taking time out of your Monday to join us. Like I said, any questions, please feel free to send them to my email, and I will do the best to get back to you as soon as possible. Yeah, thanks for your time.